So we have our next speaker. It's our last speaker for today. So let me introduce Samir Singh. He is an assistant professor at University of California, Irvine. He has, again, numerous awards, numerous best paper awards. He was selected as DARPA Riser. He won multiple challenges in different machine learning competitions. He also recently received Hellman and Noyce Facility Fellowships. So he is really well established and does a lot of interesting things. So please, Samir, it's thank you for joining us, and it's your floor.
Yeah, thank you, Nina, for the invitation. So just to be clear, everybody can hear me and see the slides, and I don't hear anyone complaining. Okay. Yeah, so welcome, everyone. Thank you for sticking around till the end of the day. I'm going to be talking about how to do explanations for machine learning predictions. This is going to be slightly different from the rest of the masterclasses, partly because it's going to be not very technical. It's going to be a high-level overview of the field. But also, I'm going to be looking into the problems with this field and potential, so sort of looking at challenges and opportunities a little bit more than just talking about the state of the art, although we'll talk about some of the methods as well. Okay, so I do want to acknowledge that a lot of this material was built in collaboration with Julius and Hema. And we have some longer tutorials at CPAIOR and Europe. So if you're really interested in this area, this talk will be an introduction, but you should go to that URL and see the rest of the material. Okay, so one of the main motivations for this work is probably a side that's fairly redundant at this point, but essentially there are lots of high-stake decisions now where machine learning is either being considered or it's already being used, along with all of our usual recommendation systems on Facebook, Amazon, and all these places, right? So the concern here is that machine learning is everywhere. And do we really understand why the predictions are made when we're trying to decide whether to use their predictions or not, right? Especially when we think about these high-stake decisions in medicine, law, and financial domains, it's kind of important to understand what the model is doing, right? So let's look a little bit more deeply into what these motivations actually are. The first motivation is a little bit more sort of practical, where you have some input that you're giving to a classifier where it looks at this image and predicts it's a Siberian Husky, and you trust the prediction, but maybe you're a little bit suspicious of what's going on. When you look at an explanation for something like this to try and understand what the model is doing, the gray part is the part that the model is not looking at. And we'll return to this example later. So you will realize that when you look at what the model is doing, even though it gets the prediction right, it's actually looking at the wrong thing. It's looking at the snow on the ground, right? And so it's looking at the wrong features to make the prediction. And so you can think about this as model understanding helping you debug models, find problems in models. But there are other reasons as well. Imagine this case where there's some defendant who sort of petitions the court, and the court decides based on some predictive model that the person is too risky to release, right? You could either trust that prediction by itself, or you can sort of look and break down why the model actually made that prediction. And this is a bit of a caricature, but you can see that this prediction is biased because it's using race and gender to make the prediction rather than the number of crimes, right? So that's a problem. And so understanding the model can help you detect biases in the model and then know when to trust the decision and when not to trust the system. Here's another example, which is slightly more on the financial side of things, where somebody has applied for a loan. The loan gets denied. The loan applicant now has to decide, okay, what should I actually do, right? When you do some kind of model understanding or explanations, you can get an explanation that says increase salary by this amount and pay credit card bills this many times, and that will change this decision, right? So now the loan applicant has some recourse. And so model understanding can help people develop these recourses so that they know what to do. Here's another example from the medicine domain where we have some data about a patient, and we send it to a predictive model. It gives us its predictions, but we can also try and understand why the model is making its predictions. And you can get model understanding that looks like these rules where it says, oh, if the gender is female and something else is going on, then predict that it's sick. Otherwise, if the gender is male, blah, 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 then it's, some other symptoms, then it's sick, right? And so maybe these features make sense, maybe they don't, but now the doctor can actually look at them and say, okay, this model is using irrelevant features for when it's predicting on females, and for the males, it looks like what I would do. So I shouldn't trust the predictions for the female. Doesn't make the model useless, because I agree that for male, it's still a useful model, right? So model understanding can help assess if and when to trust the model predictions when you're making your decisions. Okay, here's a final example where you have the same situation that I just described, but you can imagine an external authority, not just a doctor, an external authority looking at the system and saying, okay, no, this model is using an irrelevant feature, so we cannot approve it to be used in hospitals, right? So you can think about this as some kind of regulatory authority. And then again, model understanding is now helping us vet which models should be deployed in the real world. Right? So hopefully these are many different motivations, and you're convinced that we need model understanding, but there has been sort of two very different ways of achieving this model understanding. The first one is maybe a little bit more traditional one, which was to build inherently predictive models, inherently interpretable predictive models, right? So models where you can look at the structure, you can look at the parameterization, and you would know why the model is making these predictions, right? So for example, if you're doing some kind of linear regression with features that you understand, or you're building shallow decision trees, or you're writing a bunch of rules, and that's your machine learning model. And there are lots of variants of these. Then you can imagine that you would be able to understand what's going on. The other take, which is what I'm going to be focusing on today, is going to be on explaining models, right? Explaining pre-built models in almost a post hoc manner, right? So as an input, you don't have control over which model you're building. You just have some black box, some neural network, some crazy function. You give this to your explainer, which is the thing that we're going to be talking about today. And the explainer gives you something that looks like the kind of things we would do, like give a linear explanation or set of rules or a decision tree, right? Even though the original model may not be a decision tree, trying to extract one that explains, right? And that's why it's called post hoc, because we're not doing this during training. Right. There's been a lot of work on sort of which of these takes to go with. I'm just going to mention one sort of aspect to it. Those citations can give you much more details into the nuance of this whole spectrum. But essentially, there has been a trade-off that people have talked about, where there is an accuracy on one axis and how interpretable it is. And there is some evidence that these two things are difficult to attain at the same time, right? So for example, you can take existing machine learning models and you can kind of put them on a spectrum, although it's very difficult to define exactly what the y-axis is, which makes this a little bit difficult. But like linear regression may not always work for most of the applications, so the accuracy is low, but it tends to be much more interpretable because you get these coefficients and you can sort of attribute meaning to them to some extent. It's limited, but at least comparatively, it might be more interpretable. Whereas neural networks, which are these crazy deep neural networks, tend to be much more accurate, but not very interpretable, right? And so I just want to qualify that in certain settings, this accuracy interpretability trade-offs exists. And when you're working in settings where accuracy is really, really important, you tend to go with the one that's on the right-hand side of this plot. So I'm not going to talk too much more about this sort of trade-off. I really encourage you to look at Cynthia Newton's paper from 2019, who argues more for the interpretable models. But essentially, the point I agree with her is that if you can build an interpretable model, which is also adequately accurate for your setting, you should be doing that. unfortunately, I don't see it as often as we would like. So post-hoc explanations, which is what we'll be talking about today, are the ones that come to rescue. And that's why we're going to be focusing on the latter. Okay. So one word I've been throwing around is explanation. And so maybe we should think about what exactly is an explanation. The exact definition is essentially an interpretable description of the model behavior. So you have some classifier with some crazy decision surface on one side, right? So the pink and blue are sort of the decision surface even in 2 dimensions. And you have some user on the other end who wants to understand what this classifier is doing. And so the explanation sort of is the interface between the user and the classifier. And the explanation essentially has 2 goals. It has to be faithful to the classifier. So it should be explaining the classifier, not just making up an explanation, but also it should be understandable by the user. Right? That's kind of where it lies in. So what could these explanations look like? It could be anything that sort of fits this description. So maybe we can send all the model parameters of theta to the user. Sometimes that might be interpretable. And if so, then that's an explanation. Maybe the parameters are not understandable. Maybe we can just send many example predictions. As long as users can understand them and make sense of what's going on, that could be a valid explanation as well. But instead of these sort of simplistic explanations in this talk, we're going to be looking at a lot more other structures, other visual or abstract structures that summarize what the behavior would be. So for example, we can summarize it with a short program or a simple rule or a decision tree, like a flow chart, right? That would be an explanation because a user might be able to understand that much more easier than the other options. Or selecting most important features, or selecting most important points, or even describing how to flip the model prediction for any instance, right? And so on. So all of these other visualizations end up being candidates for what an explanation might look like. The other tricky thing here is that even though you're trying to be faithful, sometimes these things might be too simple. So if you want to, or on the other hand, if you want to be faithful, your explanation might get really complicated. The problem here is that if your classifier is really complicated, your explanation will also be really complicated and the user will not be able to understand. So there is an idea that sort of has become popular recently, which is to, instead of trying to explain the global classifier, explain it locally. What that means is you're given a specific instance that you care about, and the model predicts something for it. You just want to understand what that prediction is. You don't want to understand the whole classifier. That's not the point. You want to understand where that point lies on this surface, right? And so the idea is fairly simple. You look at the prediction, you look at where the point lies in the surface, and instead of trying to explain everything, you kind of zoom in, and you zoom in to some extent till what you have is something that you're comfortable explaining, right? And so the definition of a local explanation would be an interpretable description of the model behavior in a target neighborhood, which is usually a single instance. It could be a set of instances as well. Right? And so when we think about the explanation, you still have the same sort of interface you're talking about, except now you're not trying to explain the whole classifier. You're just looking at a local targeted region. And the kinds of explanations look essentially the same. You can maybe send many example predictions, summarize it with the program, features, flipping, and all of these things. Okay. So these are called local explanations. So just to sort of maybe recap the difference between local explanations and global explanations, local explanations are useful for explaining individual predictions, whereas global explanations explain the complete behavior. Local ones help unearth biases and problems in the local neighborhoods, whereas the global explanations shed light on the big picture problems with the model. And finally, the local explanations can help vet individual predictions, whether they're being made for the right reasons or not. And sometimes through local explanations, you get an idea of what's happening globally, whereas global explanations are only trying to vet the whole model at an aggregate level. Okay. So we're going to be mostly focusing on local explanations. Work on global explanations is slightly lagging behind local explanations from my view, but there has been some interesting work there. We just won't touch that too much today. All right. So here's what we're going to be talking about. I'm going to be talking about the technical quick introduction on the kinds of approaches that exist out there for explainability and sort of visually show what they kind of do. But mostly I'm going to talk about how to evaluate them, how people evaluate them. And, that's one of the biggest aspects of explanations, what limits these explainability techniques right now, and what the future challenges and just the future work in this direction looks like. Before I start, I guess, go to the next section. If there are any questions, this might be a good time to maybe chime in. Let me see. In general, I'll sort of take breaks between the big sections to see if there are any questions, or we can do them later if there aren't. Okay, cool. Let's keep going then. So let's start with the approaches to postdoc explainability techniques. I'm going to divide them into local and global explanations. We're not going to really talk about global explanations. Let's focus mostly on local explanations, where again, they're going to be split into 5 different ways of doing them. Right? Feature importance, rule-based, saliency maps, prototypes, and counterfactuals. So let's actually get started with feature importance. In this case, the methods I'm going to talk about are model agnostic in the sense that they assume you have no access to the internal structure. So you have some data point, you're literally giving it to a black box, and all you're getting out is the decision and maybe a probability, not even the gradient. Right? So you have absolutely no internal restriction access. And this is kind of nice for practical reasons. You're not restricted to any specific models. You can use any library for the model, and your explanation system is just kind of different. And you can study models that you don't even have access to. It's on some Google server somewhere. You can still access it and use it. So it's kind of nice. The problem is you're approximating something just by querying it rather than being able to look at the inside. So the first method I'll talk about is called LIME, that we introduced about 5 years ago at this point, which presents sparse linear explanation. What that means is we are essentially going to draw a line that essentially identifies what the important dimensions are. That's the sparsity part, and presents the relative importance. That's the linear part. So here's what an example looks like. This is kind of going to be a run through of what LIME actually does. You have an image here of a dog playing a guitar, and you look at the model says, oh, it's a Labrador with a fairly high probability of like 20%. What LIME does is it takes this image and creates a bunch of perturbations of that image, right? So it'll take the image, it'll hide a bunch of these things, and then it'll send it to the model, and the model comes back with some probability, maybe higher in this case than 21%. You hide some other parts, you send it again, you hide some other parts, you send it again. And you essentially create a data set of about thousands of examples like this. You send all of them to the black box model, and you see which hiding things led to an increase, which hiding things led to a decrease. And using that, you compose an explanation, right? So this is what an explanation would look like. What is nice about LIME is that it's, or maybe what's also a problem with LIME, is that it's incredibly customizable. You can change a lot of things in this whole pipeline. You can change how do you actually perturb the image or text or table or whatever domain you're working with. How do you define similarity when you're doing this locally weighted regression? That's also something you can customize. How local do you want to be? Like, how much do you want to perturb? And what is locality when you're trying to define this local explanation is something that you decide as well. And finally, how do you want to visualize or express the explanation? Which is like, are you talking in terms of features or clusters or pixels or whatever your expression is, right? And maybe it's customizable to a fault is what some people would say. So here's an example of what this looks like. This is a Husky versus wolf predicting classifier that we created. It's not just trained on unbiased data, it's trained on sort of biased data, where you can see that this model just trained in a couple of hours is actually pretty accurate. It only makes one mistake, which was that this husky is predicted as a wolf. Otherwise, it's pretty good. But when we look at Lime explanations, we've seen a bit of this before, where the gray area, the parts that the regression just gives a 0 coefficient to. You can see that wolf is predicted, every time wolf is predicted, which are these 4, the explanation only focuses on the snow. It's actually ignoring the actual model, the animal. It's only looking at the snow as what is important to make the decision. So if there is snow, so essentially we build a snow detector. If there's snow, then predict wolf, otherwise not. And that kind of explains the mistake as well, because clearly this is, it's looking at snow and husky just happens to be in the snow, but the model doesn't know that. There's a slide sort of around the same time, what became quite popular was this notion of Shapley values as also importance, which was looking at the marginal contribution of each feature toward the prediction, average over all possible permutations. So you can think of this as the perturbations that we're doing, but the actual Shapley values depend on all of the possible perturbations. And so this is in some sense a more fair way of attributing the prediction to all of the features, right? So I'm not going to go into details, but there are lots of papers here to look at, and the Scott Lundberg one is the one I would start with, that sort of describe what this looks like and the equivalence between Lime and Shapley. Okay, so these were some feature importance-based ones. Let's also briefly talk about rule-based ones that are inspired by similar ideas, but they give a different kind of explanation. The example I will talk about is anchors, which we introduced at CPAIOR a couple of years ago, where the idea is that maybe your surface is not really linear, and so you can't really find a nice linear approximation, but maybe you can still find the sufficient conditions, right? What that means is maybe we can identify the conditions under which the classifier has the same prediction, right, with high probability. So you can see that, okay, this X is right now in the pink area. I just want to find a nicely easy to understand area where it stays pink around this instance. This is a little bit abstract. Let's look at it, specific examples. So suppose you are trying to predict someone's salary. Here are a bunch of features that you're looking at, and the model predicts salary of being less than 50K with about 71% probability, 0.71, right? When you look at the Lime explanation here, it gives you a little bit of a fuzzy idea. It says that, oh, capital gain tells you that the salary should be less than 50K, but the fact that they're married suggests more than 50K, and so on, right? It gives you some idea, but it's sort of attributing it to a bunch of features. What anchors does is gives you a very simple rule. If education is less than equal to high school, then predict salary to be less than equal to 50K. That's just what the model believes, and it summarizes it with a rule. So there's been a bunch of work that looks at these rule-based explanations. Okay. There are also a bunch of approaches for postdoc explainability that do saliency maps. So here's an example. You have an input image, you send it through some model, it makes some predictions. What you want to find out are what are the most parts of the input that are most relevant for the model prediction. These methods are slightly different because they tend to look at the gradient in order to understand what's going on. There are a bunch of different words that are used to refer to this stuff: feature attribution, heat map, saliency map, depends on what you're doing. Right? There are a bunch of methods I'll quickly introduce, and then we'll talk about some of the problems. The simplest way to do this is to just look at the input gradient. So what the input gradient means is you look at the gradient of the model, not with respect to parameters, but with respect to the input image, and you get some sort of heat map, right? And the problem here, as you can see maybe in this example, is that visually the gradient just tends to be really noisy and difficult to interpret, partly because of the kind of saturations and all these kind of behaviors that happen in neural networks, which papers have shown is a problem. There are other variations like smooth grad that try to fix this by adding sort of a Gaussian noise to the input before you compute the gradient. So sort of averaging it over a bunch of like tiny perturbations. And when you aggregate the gradients, you can already see that, okay, this is actually doing a good job. It's predicting it's a junco bird because it's of the eye and how the back and the tail, wings and the feet are, for example. Right. Here's another method called integrated gradients that sort of also perturbs the input, but it does it from some baseline input. So it assumes like all 0 pixels is your baseline input, and then slowly sort of integrates from going from that baseline input to the input you care about and sort of aggregating the gradients along the way. So it's a path integral. And when you do that, you get an explanation that looks a little bit nice as well, right? And in general, there are just tons of methods, right? You can still do Lyman Sharp for these kind of images. They're computationally a little bit slow and they ignore gradients. So maybe many people don't want to do that. But there are just tons of people looking at these kind of saliency maps. So you get all kinds of different explanations when you run them, right? We talked about a few of these, but there are just many, many others that we won't go into. Okay. Our second last method of explaining is called prototypes or example-based. The idea here is not to look at features at all, but to think about explaining a model by creating or selecting inputs that are most relevant, right? There are a bunch of different approaches to this. What kind of input is the model most likely to misclassify? Which training examples are mislabeled? Which input maximally activates a neuron, and so on. The one we're going to be focusing on is called focusing on training points that are most influential and computed via influence functions. So which training points have the most influence on a test input loss, right? So the fact that we predict this is a junco bird, we want to be able to find out all of the training data points that were most responsible for this decision, right? So it would sort of probably bring up a bunch of other birds, which may or may be junco birds, right? And so you can say, oh, this is similar to this, not because of a feature, but because overall these birds look similar. And that's why the model is predicting a certain behavior. And finally, I also want to talk about counterfactuals quickly. These are a little bit similar to something we have seen with prototypes, but the idea here is to explicitly compute a recourse for affected individuals, right? So the idea behind here is thinking about the counterfactual, right? What features need to be changed and by how much to flip the model's prediction, right? So suppose you've got an unfavorable output, how do we change that? So essentially, you can imagine an applicant who's applying for a loan to some predictive model, and the model loan gets denied. What the counterfactual generation algorithm would do is look at the predictive model, look at the situation, sort of query it multiple times, essentially give the recourse to the applicant. Something like increase your salary by 50K or whatever. So the intuition here is essentially you have some X and you have some decision boundary. You want to go on the other side of the decision boundary, right? And we have two different options here because essentially that's the problem. How do you select what counterfactual to give, right? How do you choose amongst all of these candidate counterfactuals? We're not going to go into too much detail again, but essentially the idea is to find out maybe the one that's closest to you in some metric, and the closest can be defined in many different ways. You could just define it in terms of the raw feature distance between the instances. So in that case, you'll pick A here because it seems just visually closer. And you get recourses that look like this, right? You know, if your LSAT was 34.0, you would have an average predicted score, blah, 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 things like that. The problem with this minimum distance is that sometimes you get suggestions that are just not possible, right? So if your LSAT was 33.5 and you were white, you would have an average predicted score. This is not a great recourse because people can't easily, people aren't race fluid and they can't easily change their race, right? So these are just not feasible recourses to be acting on. They might still be useful as an explanation, but for someone who actually wants to do recourse, this is not very great. And so what people have done is introduced other metrics and distances that take into account the cost of changing a recourse. So cost of changing a salary versus cost of changing, paying your bills on time versus cost of changing your race, which might be impossible. Taking that cost into account, you can compute these counterfactuals and you can say things like, okay, now I'm going to give you recourses that actually make sense, right? Hey, reduce your number of credit cards and reduce your debt, and then you'll be fine. Okay. There is a lot of work in global explanations as well. A lot of them actually is based on local explanations. So taking them and collecting a bunch of them and giving them as local explanations. This work on model distillation, summaries of counterfactuals, and so on, which we're not quite going to go into, but I just want to spend a little bit time on explaining that global explanations is actually important to sort of explain the complete behavior of a black box model, right? So you tend to get a bird's eye view of what's happening. And it can really help detect big picture model biases, which are persistent across larger subgroups of the population, right? These kind of biases are often sort of impractical to look at all of the local explanations and then try to summarize in your head what's going on. And so it can be pretty useful for doing these kind of things. So in some sense, global explanations are complementary to local explanations. I wouldn't advocate for one versus the other. Depending on your use case, you might want to do either or both. Okay. So I think there are a few questions in the chat. Maybe I'll take some of them at this point and we can go back.
Maybe Joa, you can unmute and ask these questions because Joa asked a few questions.
Sure. Can you hear me? Yes.
Yeah. Mm-hmm.
So I cannot understand why you are not in your map. Why don't you call PI explanations also postdoc?
What do you mean by PI explanations?
Well, they were presented at ICHCAI 2018, and they've been studied in a number of papers. Actually, they have been even presented at ICML and NIPS papers recently.
So what does PI stand for? What do you mean by PI?
Prime implicant.
What was that?
Prime implicant.
Yeah, so I mean, I'm not trying to be completely comprehensive. I covered a bunch of them, but I would imagine if those are looking at a model and explaining them, they would be classified as postdoc as well. Yeah.
I could not understand your definition of local and global explanation. So what is exactly the difference? Concretely, if you are talking about Boolean domains, what is the difference then?
If you're talking about Boolean domains, I guess you have to think about some kind of similarity metric, right? So like you can use whatever favorite distance metric you want. And what the local explanation does, just to be clear, what a global explanation would do would give you an explanation like a program or a rule that applies to every instance in your space, right, in your domain. What a local explanation does is says, okay, I'm going to be looking at a single instance and I'm going to describe the model behavior only around some neighborhood of that instance. Right. So anything that's within, I don't know, some XL2 distance from my point, I'm just going to be looking at the classifier around that. And I'm going to define sort of what's happening in that space.
I can understand that, but then I don't understand how you do it in the case of Boolean domains.
Well, you have multiple features, and so maybe you say things like, okay, as long as only 3 features are being perturbed, I just want to look at that sort of that space. Right, it's still like Boolean, but there are many features, like maybe you have 100 features, and you just want to understand what's sort of locally relevant, as long as only 3 features are perturbed for the instance. Flipped it, I guess, in this case, right? or 4
okay.
features, or however many features you want, right? And I think let me see if any of these examples can be thought of. Like, honestly, like you can think of this as being absence or presence of any of these superpixels as sort of your Boolean domain. So in this case, we actually treat this as a Boolean domain, where we say, okay, is this piece available or not available, right? But that's maybe a little bit too local. Even a lot of these tabular domains sometimes encode features, like these features. Maybe they're not exactly Boolean, maybe some of them have multiple values, but married status in this data set is Boolean, things like that. Essentially what Lime is doing is perturbing only a subset of these rather than perturbing all of them. In the end, giving you something that says, okay, in very, very local changes, in instances that look very similar to this one, what would the model be doing? Yes, even rules like these things are local. They're not saying for every instance, if the education is less than high school, that's only when we predict 50K. It says that for this instance, the education seems to be the really most important one.
Yeah, okay.
Okay. All right.
Thank you.
Any other questions?
I think we don't have too much time. Only
Okay.
Because in the end I have to go after the talk, so I think we'll continue.
All right. Yeah, let's continue. So I'll quickly talk a little bit about the evaluation. Okay, yeah, we are definitely running out of time. Actually, what I'm going to do is I'm going to skip the evaluation and mostly talk about limits, because that are a little bit more interesting. So here are sort of the limits of explanations that we're going to be talking about today. Faithfulness, fragility, stability, and just usefulness in practice. Faithfulness is this idea that these explanation methods may not actually be reflecting what the underlying model is, right? So there's this some work people have done to show that you can take these explanation techniques that are explaining some model and coming up with some explanation. The question is, how sensitive is this explanation to changes in the model, right? Does it really depend on the input, or does it depend on the model, right? There's this kind of a question. So one thing you can do is you can change the model parameters and see what happens. So you have the original model, and then you take some parameters and you change them. Say that you take the last layer and completely randomize them. And of course, the prediction changes, but you also look at the explanation and you want to say, well, the explanation should also change, right? This is almost like a sanity check. It should just make sure it's working. When people have done that for a bunch of tasks, this is the original explanation for a bunch of explanation methods. You randomize top layer, and then you see that the explanation hasn't really changed, even though your top layer is completely random, which suggests that this explanation was maybe looking too much at the input rather than the model, right? And you can change more and more of the model. And for this specific explanation technique, changing a bunch of top layers doesn't really change the explanation, right? And you can keep this all the way. And of course, if you do it all the way to the beginning of the model, a lot of it changes, but still you can kind of see it's still not completely uniform, even if all of the weights of your model are random, right? So this was a really interesting paper that showed that the gradient has a lot to do with the input rather than just the model. And this applies across many, many different explanation techniques. So these are all, here is the original explanation, which they have slightly different ones. And here are ones when you randomize the weights. And as you randomize more and more weights, of course, some of them start looking really bad, but most of them still look pretty good, right? And there's people who've shown this for a bunch of other techniques as well. So they seem not that faithful all the time. People have also looked at fragility, where they can be easily manipulated. So here's an original image that has an explanation that seems to look reasonable. People have taken this image and manipulated that slightly. essentially so that you can control the explanation, and the explanation ends up looking something like this explanation was manipulated, right? So you can do these things just by changing the input. There's some work where people have done that you can even create classifiers where you're not changing the input, but you can create these sort of scaffolding classifiers that take your original classifier that seems to be really racist, or I guess sexist here. In this case, it's using gender as its most important feature. And you can sort of change it so that Lime and SHAP, as implemented, basically hide that feature as not being the most important one. They pick at some other feature and show that that's important. So you can effectively hide these problems. There are problems with stability as well, where you can even make non-adversarial changes to the input, and you can see a lot of change, right? So people have defined this sort of local Lipschitz constant sort of idea, where you're changing the input slightly, or however much you're changing, that goes in the denominator. And then you look at how much does the explanation change when you've slightly changed the input. And you expect that, that should be somewhat low. You don't want the explanations to change wildly just because you've changed the input a little bit. And they've done studies across a bunch of these different techniques to show that a lot of them are like 1 is where we should be. Everything seems to have a higher Lipschitz constants. Lime in particular seems to have really high ones. And again, there are other hyperparameters like the seed and patch size and blur radius and a bunch of these things that the model seems sensitive to, that you shouldn't expect it to be sensitive to. Okay. And finally, how useful it is in practice is also something that has been questioned, partly because you're trusting the layperson or the user to look at these explanations and understand what's going on, right? So in this example, it was kind of clear that, yeah, it's looking at snow because clearly snow is getting captured, but this is not a very real world example. When you actually look at the real world example, there have been people who've shown that explanations that are perfectly accurate can still mislead, right? So here's a true classifier they created, which was a simple rule-based one. But essentially in this data set, you can create an alternate explanation that is exactly the same as the original one in terms of how accurate it is to the model, but it's using other features. And so it looks less biased. Here it's using, race. Here race never shows up. And the users are very happy with this. There have also been studies showing that even though you use linear explanations as your explanation, users actually have a tough time understanding what that really means. Many humans are not able to take linear model coefficients and understand what that means, especially to diagnose model mistakes. And there have been some studies that show that, right? So those are sort of the limitations of where explainability techniques, methods seem to be struggling right now quite a bit. Okay. And in the interest of time, I'll keep going and talk a little bit about what are most exciting future directions for post-hoc explainability. I'm going to sort of split this into things that are some work has been done for a while and should be pushed a lot more, whereas other emerging directions are one that are sort of people have been looking at last year or so, not much more than that, and ones we should be looking at as well. And I probably won't go into emerging directions at all, mostly talk a little bit about the future and what that looks like. So I think in general, we need methods for more reliable post-hoc explanation techniques. A lot of the limitations I talked about make them not as reliable as we would like. They're not faithful, they are unstable, they can be fragile to all these adversarial attacks. And in general, identifying what these vulnerabilities are and proposing approaches to sort of detect them or make them less vulnerable are really, really important techniques. And people have sort of used all kinds of methods, like using Bayesian techniques to sort of capture the distribution of the data to understand what the explanation should be, or to use causal models to give more realistic explanations. There has been some work, and there needs to be more work on theoretical understanding of post-hoc explanation techniques. So for example, some people have done theoretical analysis of Lime, maybe in a simpler setup, like using a linear model as the black box, and your data is tabular and discretized, so it looks like the Boolean domain. And then essentially in these cases, trying to find what the closed form solution is for these average coefficients that Lime tries to get. And then finding out things like the coefficients seem to be proportional to the gradient of the function. And there is intuitively this makes sense, but people have shown this to be theoretically. But more importantly, showing that the local error is bounded away from zero with high probability, suggesting essentially that Lime has some error in it that you need to sort of, it always has an error, which is not a great thing. And so more theoretical analysis along this line to show that fidelity, stability, fragility, how that comes into being and how we can detect it or how we can potentially address it is extremely valuable. And hopefully some of the audience members here might be interested in doing that as well. And finally, we didn't talk about this too much, but rigorous evaluation of the utility of postdoc explanations is something that's needed. And a lot of this is on the user side, not necessarily technical. But essentially, the problem is that when people look at these explanations, either they don't understand it or they understand it and tend to over-trust it, right? So either they stay back or they over-trust. And this is maybe something that's psychological, but that's how it is. So people have shown cases where law school students trusted some underlying model like 10 times more when they see an explanation attached to it. Even though that explanation could be misleading, so you can have them trust the wrong model. And in general, data scientists tend to trust or over-trust explanations without even completely comprehending them. So once you see that there's an explanation, they're like, okay, the model is probably better because there is an explanation. That's kind of a problem. So doing a better evaluation, better rigorous studies is something that's part of what needs to happen as well. There are other emerging directions like postdoc explainability beyond classification. So looking at reinforcement learning and a bunch of these other applications of machine learning to see how to explain those. Looking at how explanations intersect with differential privacy is really important. Differential privacy itself is an upcoming field in machine learning. So whether the explanations themselves show something that's private or hopefully they don't, is something that's important to look at. And then how it intersects with fairness in models, right? If you want the model to be fair, is there a way to use explanations in order to show whether the model is fair or not, or even to give feedback on the explanation so that the model becomes fair. So that was sort of my section on the future of explainability. And that's kind of the summary of what I talked about. We didn't go into the evaluation, but we talked about a bunch of other things. And essentially, as a parting thought, I want to say that we should be thinking about the target end users that the method is supposed to be useful for. And we should be having a clear statement about what the capability or insight is of the explanation techniques, which I think it's missing right now. There's a lot of visualization and there's some technical description of what the objective is, but how does it really relate to what you want the users to take out of it? And then careful analysis, theoretical analysis and exposition of the limitations and vulnerabilities of these explanation techniques is not quite there. It's a little bit post hoc. And then, of course, rigorous user studies and using more quantitative metrics during evaluation would be good. Yeah, so I want to thank my collaborators again, Julius and Hema, on working on this material, and a lot more details and stuff will be available at that URL, including these slides as well. Okay, thank you, and I think we have time for questions.
Thank you, Samir. Do you have any questions?
I have one question. It's kind of a stupid question, but I just like to make sure I understood. Earlier, when you explained the difference between global and local, you had this example where you generate this rule from this one instance, and you say that I think the was about the earnings or something. But this rule that is then generated as an explanation, it's still global, right? So it's not like this rule only applies for this instance. Or is this the case?
It is the latter case. So I guess you can apply the same. So often what you can do is you can take the local explanation technique and apply it to the whole domain, and then you get something that's global, right? So local explanations are just saying that you define the neighborhood you want to describe the behavior in. If that neighborhood is the global space, then you get a global explanation. If that neighborhood is local, you get local explanation, right? So it's almost, you shouldn't think of it as one or the other, but it's just like, is your radius infinity, or is your radius, whatever the domain is, or is your radius something constrained? And anchors as defined can go sort of, you define the radius. So you say, like when we look at the definition here, so we are identifying the conditions under which the classifier has the same prediction in the neighborhood, right? And so if your neighborhood is local, then you get a rule that only applies locally. If your neighborhood is global, then you get a rule that applies globally. I think in this example, I'm trying to remember, I think we might have done global when we are computing this as an example of global also works. But yeah, by definition, you can go either way.
Okay, thank you.
Yeah.
But how do you actually with anchor, like already talking about like anchor, like how you define now, you have a precondition effectively. If certain features are fixed, then prediction done. So in a sense, like maybe it's a little bit confusing because this question came up a few times, whether it's a local or global. Like as it defined as an explanation, it feels like under projected features, it's global, right?
Yeah, so I think that's one of the tricky things about, so anchor maybe suffers the most from it, but a problem with all of these local explanation techniques is, what do you define as locality, right? So I could say that I want to define locality only as, at max two features can change, for example. So in that case, when you look at this thing, this says, okay, if I could only change two features, the condition is something like this, right? Like if education is the high school, it doesn't matter what the other feature I'm changing is, the salary model will predict is less than 50K. If you switch that to global, then you're saying if education is less than high school and I can change any other feature or many other features, sorry, yeah. If I can change many other features, the prediction will still be less than 50K, right?
I see. So the part kind of not explicitly shown here is how you define the distribution of the or kind of define locality.
Exactly, yeah. And then we define it a certain way. The tricky thing is also, how do you communicate that distribution to the user as part of the explanation? That's something that people don't think enough about. Yeah.
Nisrat, you had a question, please.
Yes. So. Yes, thank you for your talk. So I just have a question about you had this nice graphic for the trade-off between interpretability and accuracy. And yeah, of course, we have also no free lines there. So it's we can have sometimes also data sets where maybe random forest is better or near to neural network and so on. So is there a well-established metric to combine those two criteria?
Yeah.
My second question, maybe just, do you have also no free lines for explainability techniques too?
That's a good question. Yeah. So the tricky thing here, I think accuracy everybody understands, right? The tricky thing here is what the y-axis should be. And it's been very difficult to sort of nail down what a metric is, right? So even when we say linear regression is interpretable, in fact, it kind of depends on what your features are, right? If you're putting in conjunctions of features as input as well, right? If you have correlations in the features, or if some features are literally combinations of other features because it's not a linearly separable problem, you still don't really have interpretability in that case, right? And people have shown that if you do logistic regression with like millions of features, yeah, you get coefficients, but those don't really mean as much as people might think they mean. Maybe the sign means, but that's pretty much all. And so even the sort of interpretability of simple things is not easy to nail down. So yeah, I think this trade-off and how much it exists in general is one thing to be looking at. But I think what's more important is for the task that you care about, you would probably be able to nail down, like you said, for some cases, random forest might be more accurate, and that's fine. But in many other cases, it may not be. And it is possible that some of these more, and this is something that people have argued, especially sort of Cynthia Newton has argued, that it doesn't always have to be this trade-off. There may be cases where the more interpretable it is, the more aligned it is with the problem that you're working with, and the trade-off might actually go away. It might even get more accurate because you're actually modeling how the task should be solved or will be solved by a human or whatever it is, right? So there is that argument as well. As to your second question, I think you're right. There is sort of, it looks magical where you can just take a black box and explain it, but the problem is all of the sort of limitations we talked about, right? Like these are the things that, yeah, it may be very difficult to get these for free. And so the best solution might be to be able to at least quantify them and know in which cases not to give an explanation, because you cannot compute an accurate one in the sort of space that you're looking at.
Great, thank you.
Do we have any more questions?
Yes,
Yep.
from you.
It's
We
a
don't
little
hear you very
soft.
well.
Yeah.
Yeah, so I'm sure it might hear now. Can you hear me?
Barely.
Yeah.
And now? Better?
Maybe try a question and then we'll see what we understand.
Okay,
Yeah.
So,
If it's green, it should work. And just talk normally.
yeah.
Oh, that's better. Yeah.
Okay, yeah, so I was wondering if you look at, for instance, the picture of the lava door in the bull or husky, then you have like this algorithm that selected parts of the picture to show what are the most important features. And maybe I didn't get or hear how to select those pixels. But I was thinking, can't you just make another model that trains on selecting only parts of the picture as an input to still get the same output from the actual model, to see which pixels are given input are the most important part of the picture.
Okay, yeah. So maybe I think you're talking about this picture, and you're saying, well, what we're trying to do here is training a model to select some parts of the image and ignore the rest of the image and sort of come up with what the output looks like. Can't we train a model? Can't we design a model that does that inbuilt? And to some extent you can. People have tried to do that on pixels based cases. What we are trying to do here is actually try and explain what the model is doing. So some of these ideas are actually very difficult to do as part of the model, right? So the thing we are summarizing here is not just is this pixel by itself, or is this cluster of pixels by itself useful for the model or not. We are trying to capture correlations and a bunch of other things that are happening in the image as well. So if you were to try and make that as part of the model, you would at least have to make this clustering of pixels as part of the input. And that might look completely different across different images. And then somehow have a representation for each of these super pixels separately, which I think some people do in Vision, but it gets a little bit complicated, and it starts getting more and more complicated from there. This is a little bit simple because all we are giving here as input is still another image, just part of it is grayed out, right? And so the model can still do exactly what it's doing, you know, the decade of neural image computer vision stuff we have just completely applies directly if we try to bake it in, maybe there are ways, and people are looking into things like that. It just becomes a little bit constraining and not exactly what this is doing. Also, there may be not enough training data to train sometimes those kind of models. Whereas here, we're not training anything, we're just querying it.
Oh, yeah. So I actually meant just another model on top of this model, not like a new model.
Yeah, I don't know what that additional model might look like.
Just take a neural network that you don't understand, that you don't need to understand, that just tries to figure out which kind of parts are the most important parts, given the model you already have.
I see. Okay. Yes. So, right. Okay. Sorry about that. Yeah. So I think the question is, what if we train a model on top of this other model that we have to produce this explanation, right?
Yeah, that is.
Yeah. So to directly produce the explanation as part of its process. Okay, yeah. So people have tried to do that. I think that sort of solves the computational difficulty of computing this explanation, because you're not doing the sampling at test time. At test time, you're just given an image. The original model makes its prediction, and your explaining model generates this explanation. But then the question ends up, so you've sort of solved the computational problem of explaining, but it's not clear whether that will generalize in the right ways, and how do you explain the explainer and things like that. So there may be additional things that come up. I think people have done that a bit, especially in NLP, which I'm a little bit closer to. People have done that a lot, where there are they try to highlight part of the input as another model that predicts that. But with mixed success. Like sometimes it just points at things the model may not be looking at. Yeah, yeah, you may lose the fidelity.
Samir, related question, actually it was brought up by Guy earlier. Like you see, when you perturb, you get nonsense images in a sense. They're out of distribution images, and you still feed it to a network and then rely on the predictions the network produces to build explainable model. So what is your intuition why it works? Because you feed a lot of out of distribution images into the
so that's a good question. I think it depends on how the models behave when you give them something out of the distribution, right? So I think in computer vision, it was much easier to do than for NLP, to be honest, right? So in NLP, when you make perturbations, it gets completely out of distribution, right? Like, so a sentence doesn't make sense anymore, right? And or if you're trying to do machine translation, if I give you a garbage sentence, the model just doesn't know what to do. And so in that case, the models would behave really weirdly, and we would get weird artifacts. Even in computer vision, if we had images that were like mostly a certain color, then the model would predict, I think it was candle or something that it really liked to predict when it was blank. And yeah, that's one of the concerns here, how to sample within distribution. There have been people who've tried to sort of say, okay, how to do these perturbations while still remaining in reasonable distribution. So things like blurring the parts of the image, or replacing it with sort of in painting or sort of more advanced NLP techniques, rather than just, more advanced computer vision techniques, rather than just blanking it out. And those have sort of worked slightly better in some cases. It kind of depends on how sensitive your model is to the distribution problems. Yeah. In NLP, they were really sensitive. In computer vision, not so much. I think it's still thought of this image as being a dog image, even though a lot of it is gray and looks weird. Yeah.
Thanks. Nisut, I think you guys have to go, right? In Vienna.
Yes.
Yeah, so then let's thank Samir for the great talk. Thank you very much for joining us and for presenting. Very interesting. And because we missed important part, how to evaluate explanations, it's great that slides are online and this video will be recorded. But if you want to go for the part that was omitted due to time constraints, people can go and check.
Yeah, there are lots of videos there. So please check out that link. Thank you.
So I think we are done. Thank you everyone for participating, and thank you all the presenters.